Alright, let's look at the fundamental theorem of calculus, part 1. Alright, let's say a function is continuous on a closed interval from a to b. Alright, so if you take the derivative of the integral from a to x, right, a could be any constant, x, and f of t dt is equal to f of x. Alright, so let's prove this theorem here. Alright, so first thing I would do is I'm going to let g of x, so define a new function, which is going to be just integral from a to x, f of t dt. Right. So what we want to show is, so the fundamental theorem of calculus stated above is if you take the derivative of g of x is equal to f of x. Alright, so let's show that. So we're going to look at the derivative of g of x using the definition of derivative, which is limit as h approaches 0. Alright, then you would have g of x plus h, which is integral from a to x plus h, f of t dt, minus g of x, which is exactly that. So you have integral from a to x, f of t dt, all over h. So this is just a definition of the derivative. Alright, then we combine those integrals together on top. We're going to have limit as h approaches 0. Alright, so I'm going to just put the 1 over h like that. Alright, so when you combine this, this is going to be just an integral from x to x plus h and f of t dt. Alright, so everything boils down to finding this limit. Alright, so let's look at the picture so that we have some idea of what's going on there. Alright, so if you look at the integral from x to x plus h, f of t dt. Alright, so I drew a picture here, and this is the graph of f, and interval is going from x to x plus h. So this definite integral represents the area under this graph of f of x going from x to x plus h. So this region, the shaded region, is represented by this definite integral. Right? So we're going to find the lower bound and the upper bound of this region here. So if you look at the lowest point, looks like the lowest point is somewhere here. So what I'm going to do is I'm going to just bring it down. Actually, I can't see it. So how about, so bring it down here. Alright, so let's say at, maybe I'm going to call it t sub lowercase m to indicate the t value where the function is the smallest on that interval. And then the largest value is up here. Alright, so the maximum occurs at, let's say, I'm going to call it t sub capital M. So t sub capital M corresponds to the largest value, and t sub lowercase m corresponds to the lowest point there. All right, so you can see that if you kind of drew a rectangle, let's say using the lowest point as the height, then you draw this rectangle here, right? And as you can see that since we're using the lowest point, the area of this rectangle is going to be definitely smaller than the area of the shaded region in blue. So we know that the area is going to be base is h, right? So that's how wide it is. And height is determined by f of t sub lowercase m, all right? Then we can do an upper bound by using the highest point, and this time we're going to use the highest point. Then we're going to draw a rectangle again, and this time it's going to be a taller rectangle like that, right? So that rectangle has the area, width is base is h, and height is f of t sub capital M. All right. Then remember that we are interested in 1 over h, integral from x to x plus h, f of t dt. So we like to have 1 over h there. So what we're going to do is I'm going to just divide everyone through by h. So we get what we want to have. So divide through by h, right? So you can see that h's cancel out there, and h's cancel out there, right? To clean it up, I'm gonna actually erase those. So let's say I'm gonna erase this right here, and erase those h because we don't need them anymore. All right. So this is the lower bound and the upper bound. And what we want to do is we want to look at the limit as h approaches 0 of f of t sub lowercase m, and also the limit of f of t sub uppercase m as h approaches 0. All right. Then you can see that t sub capital M and t sub lowercase m is always between x and x plus h. So as h approaches 0, so this guy approaches 0, right? T sub capital M and t sub lowercase m approaches x. So we can rewrite it as, so this is the same limit as the limit of f of t sub lowercase m, but the t sub lowercase m approaches x. Right, same thing here. If you take the limit of f of t sub uppercase m, but the h goes, as h approaches 0, t sub uppercase m is going to approach x as well. Right? Remember that the function f is continuous. Limit and actual function value is going to be the same. So this is going to go to f of x, and same thing here. All right. Then we notice that, okay, so you have three things. You have the smallest guy, and this is the middle guy. This is the largest guy. When the smallest guy approaches f of x, and the largest guy also approaches f of x. And the middle guy has to approach f of x by squeeze theorem. So now we know the limit of this guy right here. So this is going to be f of x. So this is by squeeze theorem. Right? So this proves the fundamental theorem calculus part 1. All right. let's look at a couple examples. It's just an application of a fundamental theorem of calculus, part 1. All right, so let's take the derivative of capital F of x given here. All right, first thing I would do is I would like to switch x and pi. So in order to do that, we have to change the sign. So it's going to be negative integral from pi to x. Then everything else stays the same. So you have a square root of 1 plus secant of t with respect to t. All right. The reason why I wanted to do that is that in order to use the fundamental theorem of calculus part 1, we would have to have the lower limit to be a constant. Then you have x as the upper limit. Now we have that. All right, so if you take the derivative, capital F of x, so capital F prime of x is going to be, all right, negative sign is there, all right? So taking a derivative is basically the same equivalent to stripping the integral sign off, then make sure to put the x instead of t, all right? So we would have square root of 1 plus secant of x, right? And this is the derivative that we're looking for. All right, let's look at another example. All right, this is the combination of fundamental theorem calculus 1 and chain rule. All right, so let's take the derivative of this. So h prime of x. Right, so this is chain rule. Right, we want to take the derivative of the outside first. Then remember that here this is an inside function. Right, so taking a derivative is equivalent to stripping off the integral sign. So you would have just the inside function integrand, which is the natural log of t. So, but you have a natural log of t, but make sure to put the inside function as it is, like that. Then because of the chain rule, you would have to multiply by derivative of the inside function. Derivative of e to the x is still e to the x, so I'll put that e to the x here. All right, then you know that here natural log of e to the x is simply x, because here you have natural log and the exponential functions are inverses of each other. So these two guys essentially cancel out each other, so leaving you just x. So therefore, this is going to be x times e to the x. All right. So this is the derivative of h of x. All right. That's it. I hope that this was clear.